Between 2020 and 2024, astronomers accomplished what previous generations considered impossible, creating three-dimensional maps of the cosmic web with resolution 10 times better than anything achieved before. The Dark Energy Spectroscopic Instrument, known as DESI, began operations in 2021 at Kitt Peak National Observatory in Arizona and measured redshifts for over 40 million galaxies and quasars in just 3 years. This dwarfs every previous survey combined. The fifth generation of the Sloan Digital Sky Survey added millions more spectra. The Subaru Hyper Suprime-Cam survey and Dark Energy survey contributed deep imaging that revealed faint galaxies at distances exceeding 10 billion light-years. These massive datasets were analyzed using sophisticated machine learning algorithms trained to identify filaments, walls, voids, and clusters directly from galaxy positions. The resulting maps showed the cosmic web in unprecedented detail, and what they revealed disturbed cosmologists deeply. DESI represents a technological leap that changed observational cosmology. The instrument uses 5,000 robotic fiber positioners mounted on the 4-meter Mayol telescope. Each robot positions a fiber optic cable with millimeter precision to capture light from a specific galaxy or quasar. The entire array can reposition all 5,000 fibers in less than 2 minutes, allowing DESI to observe new targets efficiently across the sky. Every pointing captures 5,000 spectra simultaneously. These spectra measure redshifts, how much cosmic expansion has stretched light from distant objects with precision better than 30 kilometers per second. At redshift Z equals 1, where galaxies lie roughly 8 billion light-years away, this precision translates to distance uncertainties less than 1 million light-years. Over its planned 5-year mission, DESI will observe 40 million objects, creating a 3-dimensional map covering 1/3 of the sky and reaching back 11 billion years in cosmic time. The data processing challenges are staggering. DESI generates approximately 60 terabytes of raw data annually, equivalent to 15,000 hours of high-definition video. Reducing this avalanche of data to usable galaxy catalogues requires pipelines running continuously on supercomputers at Lawrence Berkeley National Laboratory and the National Energy Research Scientific Computing Center. These pipelines identify spectral lines, emission or absorption features at specific wavelengths and match them to known atomic transitions from elements like hydrogen, oxygen, and magnesium. The wavelength shift of these lines directly measures redshift, which converts to distance using cosmological models. The resulting catalogues contain precise positions and distances for tens of millions of galaxies, constructing a 3-dimensional map of cosmic structure spanning more than 20 billion cubic light-years of space. Machine learning revolutionized how astronomers extract cosmic web features from these enormous galaxy distributions. Traditional methods identified clusters simply by counting galaxies in regions and finding overdensities areas with more galaxies than average. Modern algorithms use neural networks trained on cosmological simulations to recognize filaments, walls, and voids directly from 3-dimensional positions. The DESI algorithm, developed by Thierry Sousby in 2011 and refined specifically for DESI data, traces filaments by finding ridges in galaxy density locations where density is high in 2 perpendicular directions but extended in the 3rd direction. The multi-dark algorithm identifies voids as regions where galaxy density falls below 20% of the cosmic average. The member algorithm finds galaxy clusters using both density peaks and velocity information, showing which galaxies orbit together gravitationally. Early results from DESI revealed structures that exceed theoretical size limits. In 2023, analysis of DESI's first-year data identified multiple filaments longer than 2 billion light-years, twice the scale where the cosmological principle suggests the universe should be homogeneous. The cosmological principle, a foundation of modern cosmology, states that on scales larger than about 300 to 400 million light-years, the universe should look statistically the same everywhere. One particular filament caught astronomers' attention. It connects several galaxy clusters at redshift Z, approximately 0.5, corresponding to a distance of 5 billion light-years, and extends 2.3 billion light-years in length, while measuring only 80 million light-years in width. This makes it nearly 30 times longer than wide. Standard lambda CDM simulations, the current best model of cosmic structure formation, rarely produce filaments this extreme at this redshift. The discovery prompted immediate reanalysis to check for projection effects, where multiple shorter filaments might align by chance along our line of sight, creating the illusion of a single giant structure. But three-dimensional analysis, accounting for redshift space distortions, confirmed the filament's physical reality. It genuinely spans 2.3 billion light-years. The existence of this structure, and others like it, suggests either we're observing rare statistical fluctuations at the extreme tail of what lambda CDM allows, or something about our understanding of structure formation is incomplete. Neither possibility is comforting for cosmologists, who have spent decades refining models that successfully explain most cosmic structure. The Subaru Hyper Suprime-Cam survey added crucial weak gravitational lensing data that revealed dark matter distribution across the cosmic web. Gravitational lensing occurs when massive objects bend light from background sources, a prediction of Einstein's general relativity confirmed countless times. By measuring tiny shape distortions in hundreds of millions of distant galaxies, astronomers map foreground mass concentrations including dark matter, which comprises 85% of all matter but emits no light. The HSC survey covers 1,400 square degrees of sky to depths that detect galaxies at redshifts Z equals 2 to 3, creating dark matter maps spanning several billion light-years. These maps reveal dark matter filaments connecting clusters and dark matter halos surrounding individual galaxies. Comparing dark matter maps with visible galaxy maps shows how well galaxies trace underlying dark matter, a critical test of structure formation theory. Disturbingly, some filaments show dark matter concentrations 20 to 30% higher than lambda CDM simulations predict for comparable structures. The Dark Energy Survey, which completed observations in 2019, provided complementary data crucial for understanding these anomalies. DESI photographed 5,000 square degrees of southern sky, detecting 300 million galaxies and measuring distances for millions using photometric redshifts estimates based on galaxy colors rather than spectra. Photometric redshifts are less precise than spectroscopic redshifts, typically uncertain by 2 to 5%, but they allow surveying vastly more galaxies efficiently. DES combined weak gravitational lensing analysis with galaxy clustering measurements to constrain cosmological parameters. The results showed troubling discrepancies. The universe appears measurably less clumpy than the Planck satellite's observations of the cosmic microwave background predict. This discrepancy, known as the S8 tension, reached statistical significance around 2.5 to 3 sigma, suggesting either systematic errors in measurements or new physics beyond lambda CDM. Combining datasets from multiple surveys amplifies statistical power but also revealed disturbing inconsistencies. DESI provides precise distances for millions of galaxies through spectroscopy. DES and HSC provide weak lensing measurements, mapping total matter, including dark matter. The Planck satellite provides cosmic microwave background data showing initial conditions 380,000 years after the Big Bang. Cross-correlating these datasets tests internal consistency. Do different measurements of the same physical quantity agree? Disturbingly, several cross-correlations show 2 to 3 sigma discrepancies, differences unlikely to occur by pure chance, but not yet reaching the 5 sigma threshold physicists typically require for claiming definitive discovery. For example, correlating DESI galaxy positions with DES weak lensing measures how strongly galaxies cluster within dark matter halos. The measured correlation is 15% weaker than lambda CDM predicts, suggesting either galaxies cluster less than expected or dark matter halos are less concentrated than models assume. The three-dimensional maps reveal cosmic structure's hierarchical organization, but with unsettling irregularities that don't match simulations. Galaxies cluster into groups averaging 10 galaxies. Groups cluster into larger structures called clusters containing 100 to 1,000 galaxies. Clusters connect along filaments spanning hundreds of millions of light years. Filaments surround voids, vast underdense regions billions of light years across. This hierarchy matches theoretical predictions qualitatively, but quantitative comparisons reveal systematic mismatches. Voids are consistently larger and emptier than simulations predict. Filaments are denser and more sharply defined than models suggest. The largest structures, great walls spanning billions of light years, and massive superclusters appear at scales where they shouldn't exist according to inflationary cosmology, which predicts a specific maximum scale for structure based on the observable universe's size at inflation's end, roughly 10 to the minus 32 seconds after the Big Bang. The unprecedented resolution allows studying how cosmic structure evolved over time. By comparing structure at different redshifts equivalently, different cosmic epochs, astronomers see the cosmic web's assembly history. At redshift Z equals 2, when the universe was 3 billion years old, filaments were thinner and voids smaller than today. By Z equals 1, around 6 billion years ago, structures resembled their current configuration, but with contrast between overdense and underdense regions, about 20% weaker. From Z equals 1 to present, structure evolution slowed noticeably as dark energy began dominating cosmic expansion, opposing gravitational collapse. This evolutionary timeline matches lambda CDM predictions at low redshift fairly well, but mismatches appear at Z greater than 1.5, where structures appear more evolved, featuring more massive clusters and larger voids than models predict, given the time available for gravity to amplify initial fluctuations. The transformation from data-starved to data-rich science changed cosmology fundamentally. Earlier surveys mapped thousands, or at most hundreds of thousands of galaxies. DESI maps tens of millions, a 1,000-fold increase in sample size. This enormous statistical power allows detecting subtle effects previously hidden by noise. Rare structures, the largest filaments, deepest voids, most massive clusters now appear in sufficient numbers for rigorous statistical analysis. Previously, finding one structure exceeding theoretical size limits was ambiguous. Perhaps just a statistical fluke, the 1 in a million rare fluctuation allowed by models. Finding dozens of such structures crosses a threshold. It transforms an anomaly into a pattern-demanding explanation. The cosmic web maps, created between 2020 and 2024, revealed patterns that disturbed cosmologists precisely because they showed familiar phenomena pushed to extremes, challenging theoretical frameworks carefully constructed. over decades. The universe is more asymmetric than theory predicts. The cosmological principle stands as a foundation of modern cosmology, proposed by Alexander Friedmann in 1922 and supported by Edwin Hubble's observations showing uniform cosmic expansion. This principle states that the universe is both homogeneous and isotropic on sufficiently large scales. Homogeneous means matter distributes uniformly. On average, any sufficiently large region should contain roughly the same matter density. Isotropic means the universe looks statistically the same in all directions, no preferred axis or special orientation exists. The critical scale where homogeneity emerges is generally accepted to be about 300 to 400 million light-years or 100 megaparsecs. Below this scale, structure like galaxies, clusters, and filaments creates obvious inhomogeneity. Above this scale, the universe should become a smooth, featureless distribution, but recent cosmic web maps reveal disturbing asymmetries persisting to scales exceeding 3 billion light-years, 10 times larger than where homogeneity should dominate. These asymmetries raise fundamental questions about whether the cosmological principle truly describes our universe or merely approximates reality within limited observational horizons. The most striking asymmetry is a dipole in structure distribution. One hemisphere of the sky contains approximately 10% more large-scale structures than the opposite hemisphere. This discovery emerged in 2020 when Nathan Seacrest and colleagues analysed 1.36 million quasars from the CatWise 2020 catalogue, an all-sky infrared survey combining data from NASA's WISE and NEOWISE missions. Quasars are extremely luminous active galactic nuclei, powered by supermassive black holes accreting matter at prodigious rates, visible to enormous distances. Seacrest's team found that quasar density varied systematically across the sky, in a pattern matching a dipole. Higher density in one direction, progressively lower density in the opposite direction. The dipole's amplitude significantly exceeded what Earth's motion through space should produce. The cosmic microwave background shows a dipole caused by our motion at 370 km per second toward the constellation Leo, but the quasar dipole, if interpreted as caused by motion, would require velocity exceeding 1,000 km per second, impossible to explain by local gravitational attraction from nearby structures. The statistical significance of this dipole is deeply troubling. Analysis showed 3.9 sigma significance, meaning the probability of such a dipole occurring by pure chance in an isotropic universe is roughly 1 inch 10,000. Further analysis using an extended catalogue containing 2.7 million quasars confirmed and strengthened the dipole to 4.2 sigma significance. The dipole direction points approximately toward right ascension, 150 degrees, declination, -10 degrees, close to but not exactly aligned with the CMB dipole direction at right ascension, 168 degrees, declination, -7 degrees. This misalignment is puzzling. If both dipoles resulted from our motion through space, they should point exactly the same direction. The discrepancy suggests the quasar dipole reflects genuine asymmetry in structure distribution, rather than a kinematic effect from motion. Explaining a 10% density variation across the entire sky requires structures exceeding 30 billion light-years in extent larger than the observable universe's diameter of 93 billion light-years, which should be physically impossible. Radio galaxies independently show a similar dipole pattern. In 2022, Ashok Singhal analysed 1.4 million radio sources from the NVSS and SUMS surveys, comprehensive radio sky surveys, covering the northern and southern hemispheres, respectively. His analysis found a dipole with 5.1 sigma significance, extremely unlikely to occur randomly, with probability less than 1 inch several million. The radio galaxy dipole points toward right ascension 170 degrees, declination -7 degrees, close to the quasar dipole, but again not precisely aligned with the CMB dipole. The amplitude corresponds to velocity exceeding 1,500 km per second, if interpreted as kinematic effect from our motion. Such high velocity is inconsistent with observations of galaxy velocities in our local cosmic neighborhood, which show bulk flows at most 600 to 800 km per second, measured through various techniques. The implication is disturbing. The radio galaxy dipole represents true asymmetry in how structure distributes across the observable universe, rather than motion artifact. Galaxy cluster dipoles add another layer of confusion to this puzzle. Studies using cluster catalogues compiled from ROSAT X-ray observations, Planck-Sunyaev-Zeldovich surveys detecting hot gas in clusters, and optical surveys identifying clusters through galaxy overdensities find dipoles with 2 to 3 sigma significance. However, these cluster dipoles point in various directions, not consistently aligned with either the quasar or radio galaxy dipoles. This directional scatter deepens the mystery considerably. If all dipoles resulted from genuine cosmic asymmetry, some enormous structure or density gradient stretching across the observable universe, they should align because they all trace the same underlying matter distribution. If they resulted from our motion through space, they absolutely must align, since motion has a single, well-defined direction. The fact that different tracers show dipoles pointing different directions suggests either systematic errors affecting each survey differently in ways not yet understood, or cosmic structure is so irregular that different galaxy populations sample different aspects of asymmetry, yielding different apparent dipole directions. Theoretical explanations struggle to account for observed dipole amplitudes without violating fundamental cosmological principles. In lambda CDM, structure distributes randomly around a homogeneous mean. Random distributions always exhibit some asymmetry. If you divide the sky arbitrarily into hemispheres and count galaxies, the numbers won't match exactly. But the expected asymmetry from random fluctuations is small, approximately 1 divided by the square root of n, where n is the number of independent structures. With millions of quasars sampling the universe, expected asymmetry is roughly 1 inch, 1,000, or 0.1%. Observed asymmetry is 10%, 100 times larger than random expectation. Explaining this requires either we happen to occupy a very unusual location, perhaps at the center of a huge underdensity or overdensity, or the universe fundamentally isn't isotropic, as the cosmological principle assumes. Both possibilities are uncomfortable for different reasons. The asymmetry persists to remarkably high redshifts. Analyzing quasar distributions at different redshifts shows the dipole exists at z equals 0.5, z equals 1.5, and z equals 2.5, corresponding to look-back times of 5 billion, 9 billion, and 11 billion years respectively. The dipole doesn't wash out or weaken at greater distances, as expected if it resulted from local structure within a few billion light-years. Instead, it maintains similar amplitude across all redshift bins examined. This persistence to high redshift is particularly disturbing because inflation, the rapid exponential expansion during the universe's first fraction of a second, predicts that fluctuations should freeze at scales exceeding the cosmic horizon at inflation's end. Structures larger than this fundamental scale shouldn't exist in standard inflationary models, yet the dipole's persistence suggests correlated structure spanning at least 10 billion light-years, approaching the observable universe's size and challenging inflationary cosmology's predictions about maximum structure scales. Some cosmologists question whether these dipoles are genuine or artifacts of systematic errors. Sky coverage is incomplete. Large survey gaps exist due to galactic plane obscuration, where dust in the Milky Way's disk blocks distant objects, and survey footprints don't uniformly cover the entire sky. If surveys preferentially miss or include certain sky regions, artificial asymmetries could appear. Galactic extinction varies across the sky. Dust absorbs light more strongly in some directions than others. If extinction corrections are imperfect, they might mimic genuine density variations. Observational selection effects, where surveys detect bright objects more easily in some regions than others due to varying sensitivity, background contamination, or observing conditions, could create false dipoles. Multiple studies have tested extensively for these systematics, applying sophisticated corrections and using different, independent datasets. The dipoles persist after these corrections, but some skepticism remains. Extraordinary claims require extraordinary evidence, and genuine, large-scale isotropy violation would be extraordinarily revolutionary, overturning a century of cosmological modelling. If the dipoles are genuine, the implications for cosmology are profound and unsettling. The cosmological principle's validity underpins essentially all cosmological modelling: Big Bang theory, cosmological distance calculations, interpreting supernova observations, interpretations of cosmic microwave background fluctuations, dark energy evidence, even the universe's age and expansion rate. If the principle is wrong, if the universe is significantly anisotropic on the largest observable scales, then cosmological models require fundamental revision from the ground up. Distance measurements might be systematically incorrect because they assume homogeneity when calculating how redshift relates to distance. Dark energy evidence, inferred partly from supernova distances, might be partly artifact of incorrect distance assumptions in an inhomogeneous universe. The universe's age and expansion rate might differ from standard values derived, assuming homogeneity. These implications make cosmologists understandably reluctant to abandon the cosmological principle without overwhelming evidence. Current evidence dipoles at 3 to 5 sigma significance is strong and troubling, but not yet at the 5 sigma level particle physicists require for definitive claims. Confirmation from future surveys and deeper understanding of systematics remains critical. The cosmic voids are too large and too empty. Cosmic voids are vast, underdense regions where galaxies are rare, occupying roughly 80% of the universe's volume. In standard lambda CDM models, typical voids span 100 to 300 million light-years in diameter, with occasional supervoids reaching perhaps 500 to 800 million light-years. These predictions emerged from decades of simulations modelling how initial density fluctuations evolve under gravity and cosmic expansion. But observations consistently find voids exceeding these sizes, sometimes dramatically. The KBC void, named after discoverers Ryan Keenan, Amy Barger, and Lennox Cowie, who identified it in 2013, potentially reaches 2 billion light-years in diameter if their interpretation is correct. This would make it one of the largest structures in the observable universe. Even more disturbing than size alone, voids are consistently emptier than lambda CDM predicts, containing 50 to 70% fewer galaxies than simulations suggest should populate regions of comparable underdensity. The Botez void provides a well-studied example of excessive emptiness, discovered in 1981 by Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Schechtman during galaxy redshift surveys. This void spans approximately 330 million light-years in diameter and lies about 700 million light-years from Earth, in the direction of the constellation Boötis. Initial surveys found almost no galaxies within it, an eerie, empty bubble in the cosmic web. More sensitive modern surveys, including SDSS, have searched deeper, identifying 60 large galaxies within the void's volume. Sounds like a lot until you calculate what density this represents. Only about 2% of the expected galaxy density based on cosmic average. A typical region this size should contain thousands of galaxies. The Botez void contains 60. This extreme emptiness, 98% below average density, is more severe than lambda CDM simulations typically produce. Simulations predict voids of this size should retain at least 5 to 10% of average density, not 2%. The local void demonstrates that emptiness exists uncomfortably close to home. This void extends from about 10 to 100 million light-years from the Milky Way in the direction away from the Virgo cluster and contains remarkably few galaxies. Being nearby allows detailed study impossible for distant voids. Surveys have catalogued perhaps 10 to 15 dwarf galaxies in the local void's volume, a region that should contain several hundred galaxies based on cosmic average density. Even accounting for observational difficulties detecting faint dwarf galaxies, the local void is clearly severely underdense. More disturbing, 21 centimeter radio observations detecting neutral hydrogen gas find large regions within the local void containing no detectable gas whatsoever. This extreme gas depletion suggests matter evacuation was nearly complete. Gas flowed out into surrounding filaments and walls, leaving behind an emptier void than theoretical models predict. Statistical analyses quantify the excess of large voids disturbing cosmologists. By counting voids larger than 1 billion light-years identified in surveys like SDSS and comparing with predictions from lambda CDM simulations run with cosmological parameters matching Planck satellite observations, researchers find observations exceed predictions by factors of 3 to 10 depending on exact void definitions used. If lambda CDM is correct, surveys should find perhaps 1 to 3 voids exceeding 1 billion light-years in the surveyed volume. Observations find 10 to 30 depending on identification algorithm. The discrepancy reaches 2 to 3 sigma statistical significance, unlikely by pure chance but not definitively ruling out lambda CDM. The significance depends sensitively on void-finding algorithms and definitions. More permissive algorithms, counting loosely connected underdense regions as single voids, find more large voids. Stricter algorithms requiring spherical, isolated underdensities find fewer. But across all reasonable definitions, observations consistently show excess large voids compared to standard predictions. Void emptiness statistics compound the size problem. For voids of any given size, lambda CDM predicts specific density contrasts. How much less dense the void interior should be compared to cosmic average. These predictions depend on cosmological parameters like matter density, dark energy density, and initial fluctuation amplitude. Observations systematically show voids are emptier than predicted by 20 to 50%. A void 300 million light-years across should retain roughly 15% of average galaxy density, according to simulations. Observations find 5 to 10%. This consistent offset suggests systematic failure of models to predict void properties accurately. Possible explanations include that void galaxy surveys miss faint dwarf galaxies, making voids appear emptier than they truly are. But modern surveys sensitive to quite faint galaxies still find the discrepancy, arguing against simple observational bias. Alternatively, galaxy formation might be suppressed in voids more strongly than models account for, with environmental effects preventing gas from collapsing to form stars efficiently in underdense regions. The abundance of the largest voids probes cosmology sensitively. Standard lambda CDM predicts an exponential cutoff in the void size distribution. Voids above certain sizes become exponentially rarer. The cutoff scale depends on cosmological parameters, particularly the amplitude of primordial density fluctuations and dark energy's density and equation of state. Observations show the void distribution's tail extends farther than predicted. The cutoff scale is larger, meaning bigger voids are less rare than expected. Interpreting this requires either increasing initial fluctuation amplitudes, which would contradict cosmic microwave background observations showing fluctuations at the 1-inch 100,000 level, or modifying structure formation physics. Perhaps dark energy plays a stronger role in void expansion than standard models assume, or matter clusters on large scales differently than lambda CDM predicts. Neither explanation is straightforward, and both require modifications to the standard cosmological model. The KBC void's reality and implications remain controversial and actively debated. If the Milky Way truly lies within or near the edge of a 2 billion light-year underdensity, this has profound implications for interpreting cosmological observations. Locally measured expansion rates, the Hubble constant determined using Cepheid variable stars and type Ia supernovae, might exceed the cosmic average because voids expand faster than average regions due to weaker gravitational star deceleration. This could explain 2 to 3 km per second per megaparsec of the Hubble tension, the disturbing 5 to 6 sigma discrepancy between local measurements, giving 73 and cosmic microwave background predictions giving 67.4. But different analyses using different galaxy catalogues and void-finding algorithms reach different conclusions about the KBC void. Some find strong evidence for a 2 billion light-year void. Others find only modest underdensity, at most 500 million light-years across. The disagreements stem from fundamental challenges defining where voids begin and end, and determining whether multiple smaller voids should be considered one giant structure or separate entities. Some cosmologists propose that void anomalies result from improper comparison between observations and simulations. Simulations predict dark matter void distributions, where dark matter, which comprises 85% of all matter, is underdense. Observations measure galaxy void distributions, where visible galaxies are sparse. If galaxies trace dark matter imperfectly, particularly in voids where galaxy formation efficiency is low and environmental effects might prevent gas from forming stars efficiently, then galaxy-based void surveys might identify voids larger and emptier than they truly are when considering total matter, including dark matter. Testing this hypothesis requires comparing galaxy void statistics with weak gravitational lensing void statistics. Voids identified through underdensities in lensing signal which traces total matter, including dark matter. Preliminary comparisons show voids appear similarly extreme in both lensing and galaxy surveys, suggesting the anomaly isn't purely a galaxy formation effect. The voids genuinely are too large and too empty when considering all matter, not just visible galaxies. The disturbing aspect of void anomalies is their persistence despite extensive theoretical and observational investigation. These aren't subtle effects requiring sophisticated statistical techniques to detect. Voids are obviously larger and emptier than standard predictions. Cosmologists have proposed numerous solutions: modified initial conditions, alternative dark energy models, modifications to gravity on large scales, non-standard dark matter properties, environmental effects on galaxy formation. None fully resolves the discrepancies without creating tensions elsewhere. The voids challenge lambda CDM in ways that don't have simple fixes. They hint that something about how we model large-scale structure formation, perhaps the nature of dark energy, perhaps dark matter's properties, perhaps initial fluctuations' statistical properties, differs from standard assumptions in ways not yet understood. The filaments are far denser than expected. While voids are too empty, filaments show the opposite problem. They're too dense. Weak gravitational lensing observations from the Subaru Hyper Suprime-Cam survey and Dark Energy survey reveal that dark matter density in filament cores is 20 to 30% higher than lambda CDM simulations predict for. Filaments of comparable length and width. The warm-hot intergalactic medium, known as WIM, is diffuse gas-filling filaments at temperatures between 100,000 and 10 million Kelvin. This gas is detected through X-ray emission and ultraviolet absorption lines imprinted on spectra of distant quasars whose light passes through the WIM-WHIM. Temperature measurements show values about 50% hotter than standard predictions. Observed temperatures reach 6 to 8 million Kelvin in some filaments, where models predict 4 to 5 million Kelvin. Even more surprising, magnetic fields in filaments measured through radiosynchrotron emission from relativistic electrons and Faraday rotation of polarized radio waves reach 50 to 200 nanotesla, roughly 100 times stronger than lambda CDM. Simulations including magnetohydrodynamics predict the strongest evidence for excess filament dark matter comes from weak lensing measurements requiring exquisite precision. In 2022, Taehyun Shin and colleagues analyzed Hyper Suprime-Cam data measuring lensing signals from approximately 1,000 filaments identified between galaxy cluster pairs separated by 100 to 300 million light-years. Weak lensing measures how foreground mass, both visible and dark matter, distorts shapes of background galaxies through gravitational light bending. The lensing signal strength directly measures total mass in the foreground structure. Results showed filament masses exceeding lambda CDM predictions by factors of 1.2 to 1.3, meaning 20 to 30% excess. The statistical significance is 2.8 sigma, unlikely by chance, but not reaching the 5 sigma gold standard. The excess doesn't result from incorrectly including cluster outskirts, as filament analyses carefully excluded regions within 30 million light-years of clusters. It represents genuine excess mass in filament bodies between clusters. Independent confirmation came from the Dark Energy Survey in 2023. Judith Pratt and colleagues measured weak lensing signals from approximately 500 filaments identified in DESI galaxy data using background galaxies detected in the same survey. They found filament masses 25% higher than lambda CDM predictions with 2.5 sigma significance. The consistency between HSC and DES measurements is significant because these surveys use completely different telescopes, observe different sky regions, use different galaxy samples, and employ different analysis pipelines. The probability both surveys suffer identical systematic errors producing the same spurious 20 to 30% excess is extremely low. When results from both surveys are combined statistically, the significance increases to 3.2 sigma, crossing into troubling territory where dismissing the excess as statistical fluctuation becomes increasingly difficult. This filament dark matter excess creates a fundamental paradox. If filaments contain 20 to 30% more dark matter than predicted, where did this extra mass originate? The total matter in any large region, filaments plus voids plus clusters, is fixed by cosmic average density, which is well measured through multiple independent techniques, including cosmic microwave background observations, baryon acoustic oscillations in galaxy clustering, and Big Bang nucleosynthesis predictions of primordial element abundances. More matter in filaments requires less matter somewhere else. Presumably voids or diffuse regions between filaments are even more underdense than observations directly indicate, compensating for filament overdensity. But voids already appear too empty based on galaxy counts. If voids are even emptier in total mass, including dark matter, than galaxy distributions suggest, the discrepancy worsens rather than resolves. The resolution might be that diffuse regions between filaments, not classified as either filaments or voids in typical algorithms, are significantly underdense. But mapping these intermediate density regions accurately is challenging, leaving the mass budget paradox unresolved. WIM temperature measurements provide independent evidence for excess filament matter through a different physical channel. When gas falls into filaments' gravitational potential wells, it heats through gravitational compression and shocks where gas streams collide. The equilibrium temperature depends on potential well depth, which depends on total mass. If filaments have 20 to 30% more mass than predicted, their deeper potential wells should produce hotter WHIM. Observations confirm this. Chandra X-ray observatory detections of oxygen emission lines from WHIM show temperatures reaching 6 to 8 million Kelvin in filaments, where lambda CDM predicts 4 to 5 million Kelvin, roughly 50% excess. The Cosmic Origins spectrograph on Hubble Space Telescope detects oxygen absorption lines in distant quasar spectra, showing WIM at temperatures 300,000 to 500,000 Kelvin compared to predicted 200,000 to 300,000 Kelvin. The 50% temperature excess matches expectations from 20 to 30% mass excess via gravitational heating, providing consistent evidence across completely independent observational techniques. Magnetic field strengths in filaments disturb theorists because they're so unexpectedly strong and difficult to explain. Magnetic fields shouldn't exist in primordial gas. They must be generated through dynamo processes where plasma motions create and amplify fields. In filaments, turbulence from galaxy motions, gas flows, and shocks powers dynamos. Lambda CDM simulations, including magnetohydrodynamics and sophisticated treatments of dynamo physics, predict filament fields around 1 to 10 nanotesla. But observations measuring Faraday rotation, how magnetized plasma rotates the polarization angle of radio waves passing through show fields of 50 to 200 nanotesla in numerous filaments. The discrepancy of 10 to 100 times is enormous, suggesting either observational errors not yet identified, computational limitations in simulations preventing accurate magnetic field evolution modeling, or fundamentally different magnetic field generation and amplification mechanisms than models assume. The 2021 detection by Tessa Wernstrom and colleagues using the Low-Frequency Array Radio Telescope provided particularly striking evidence for strong filament magnetic fields. The team stacked radio signals from 10,000 galaxy pairs selected such that pairs were separated by 100 to 200 million light-years distances where filaments should connect them. Stacking improves signal-to-noise by averaging weak signals from many filaments. The stacked signal showed clear synchrotron emission radio waves emitted by relativistic electrons spiraling in magnetic fields from the filaments themselves. The emission intensity indicated magnetic field strengths around 100 nanotesla. This detection confirmed earlier tentative measurements and provided robust statistical evidence that filaments contain strong magnetic fields, vastly exceeding standard predictions. The field strengths implied dynamo processes operate far more efficiently than understood, or that primordial magnetic fields present in the early universe before structure formation seed filament fields, which are then amplified during gravitational collapse. Galaxy streaming velocities in filaments provide yet another independent measure showing excess. Galaxies in filaments move along filaments toward clusters at typical velocities 200 to 400 km per second. These streaming velocities result from gravitational acceleration toward clusters and depend on filament and cluster masses. Lambda CDM predicts streaming velocities based on structure masses and gravitational dynamics. Observations from galaxy redshift surveys measuring both line-of-sight velocities through redshifts and transverse velocities through proper motions show velocities 10 to 15% higher than predicted. A 15% velocity excess suggests roughly 30% mass excess if streaming velocities scale as square root of mass, as simple gravitational dynamics suggests. The velocity measurements are independent of weak lensing mass measurements, providing corroborating evidence through completely different physics. Higher velocities might also explain some anomalies in redshift space clustering measurements, where peculiar velocities distort apparent galaxy distributions. Some studies find baryon fraction inconsistencies, adding further confusion. The cosmic baryon fraction ordinary matter versus dark matter is approximately 16% based on Big Bang nucleosynthesis, calculating primordial element abundances and cosmic microwave background observations, measuring matter and big radiation densities. Every region should contain this ratio. Filaments should have 16% baryons, 84% dark matter. But some studies measuring both dark matter through weak lensing and baryons through X-ray emission or Sunyaev-Zeldovich effect, detecting hot gas, find baryon fractions 12 to 14% in filaments lower than cosmic average. This deficit suggests baryons concentrate less in filaments than dark matter, residing more in lower density regions, or in forms difficult to detect, like warm gas or ionized hydrogen. Alternatively, systematic errors in mass measurements might bias results. The baryon fraction puzzle is less statistically significant than the dark matter excess, but adds to accumulating evidence that filament properties mismatch expectations. State-of-the-art cosmological simulations struggle to reproduce observed filament properties despite enormous computational resources. The illustrious TNG, Eagle, and Magneticum simulations represent the current pinnacle of cosmological modelling, including dark matter, gravity, gas, hydrodynamics, star formation, feedback from supernovae and active galactic nuclei, magnetic fields, and numerous other physical processes. These simulations run on supercomputers for months, evolving billions of particles through cosmic time. Yet when simulation predictions for filament properties are compared with observations, systematic discrepancies appear across multiple independent observables. Dark matter density profiles in filament cores are too low by 20 to 30%. WIM temperatures are too low by 30 to 50%. Magnetic field strengths are too low by factors of 10 to 100. Galaxy streaming velocities are too low by 10 to 15%. The consistency of these discrepancies across different properties and different simulations suggests the problem isn't computational resolution or specific modeling choices, but missing physics or incorrect assumptions about initial conditions, dark matter properties, or dark energy behavior, the Hubble tension, and structure anomalies. The Hubble tension represents cosmology's most pressing crisis. Local measurements using Cepheid variable stars and type Ia supernovae yield H0 equals 73 to 74 km per second per megaparsec, meaning a galaxy 1 megaparsec, or 3.26 million light-years away, recedes at 73 to 74 km per second due to cosmic expansion. Cosmic microwave background observations from the Planck satellite predict H0 equals 67.4 plus or minus 0.5 km per second per megaparsec, assuming lambda CDM cosmology is correct. The 5 to 6 sigma discrepancy between these values, a difference of 6 to 7 km per second per megaparsec, cannot reasonably be attributed to measurement errors, given the precision achieved by both techniques. Either systematic errors affect observations in ways not yet understood, or lambda CDM cosmology is incomplete or incorrect. Disturbingly, structure anomalies like excessive voids and dense filaments might contribute to the tension, suggesting local measurements don't sample the true cosmic average expansion rate. Local measurements build on the cosmic distance ladder, a carefully constructed series of methods extending from nearby to distant objects. The foundation is geometric parallax, measuring distances to stars within 300 light-years, using Earth's orbital motion, creating apparent stellar position shifts. Second rung uses Cepheid variable stars, pulsating stars whose periods relate directly to intrinsic luminosity through the Leavitt law discovered by Henrietta Leavitt in 1912. By measuring Cepheids' apparent brightness and knowing intrinsic luminosity from periods, distances to galaxies within 100 million light-years are determined. Third rung uses type Ia supernovae, exploding white dwarfs with remarkably uniform peak luminosity around 5 billion solar luminosities. Measuring supernova distances out to 1 billion light-years and comparing with redshifts measures expansion rate, the Hubble constant. Adam, Rees, and colleagues have refined this ladder, achieving 1.5 to 2% precision, consistently finding 0, approximately 73. The Planck satellite measured cosmic microwave background temperature fluctuations with extraordinary precision from 2009 to 2013. These fluctuations encode information about cosmic conditions 380,000 years after the Big Bang, when photons decoupled from matter. The fluctuation pattern depends on cosmological parameters: matter density, dark energy density, curvature, and expansion rate. Lambda CDM provides equations relating these parameters derived from Einstein's general relativity. Given observed fluctuation patterns, lambda CDM predicts H0 should be 67, for with uncertainty only 0.7%. This prediction assumes lambda CDM is correct. If the model is wrong or incomplete, the inferred 0 is wrong. Planck's measurement achieved remarkable precision through all sky coverage at multiple frequencies, allowing removal of foreground contamination from our galaxy and comprehensive, systematic error analysis. The result is robust within lambda CDM's framework. The tension persists despite intense scrutiny searching for systematic errors. Local measurements could be biased if Cepheid distance calibrations are incorrect, or if type Ia supernovae aren't as uniform as assumed. But independent distance methods, using tip of the red giant branch stars, measuring luminosity of brightest red giants as standard candles, surface brightness fluctuations, measuring integrated brightness variations in distant galaxies, and gravitational lensing time delays measuring delays between multiple images of lensed quasars all yield HAZARO, consistent with Cepheids and supernovae, clustering around 73. These methods involve completely different systematics, yet converge on similar values. Planck measurements could be biased if foreground emission from our galaxy contaminates the cosmic microwave background signal, or if instrumental calibration is incorrect. But ground-based CMB experiments, like the Atacama Cosmology Telescope and South Pole Telescope, using different instruments and analysis techniques, measure HAZARO approximately 67, confirming Planck. The persistence across multiple independent methods on both sides deepens the crisis. Structure anomalies might contribute meaningfully to Hubble tension. If we live in or near a large underdense region, like the proposed KBC void, local expansion could exceed cosmic average. Underdense regions expand faster because less matter means weaker gravity, providing less deceleration. Detailed calculations using realistic void density profiles show that an observer in a 2 billion light-year void with 20 to 30% underdensity would measure HAZARO approximately 2 to 3 kilometers per second per megaparsec, higher than the true cosmic average. This could explain roughly half the tension, reducing the discrepancy from 6 down to 3 or 4 kilometers per second per megaparsec. The remaining 3 kilometers per second per megaparsec would require additional explanations, perhaps early dark energy or modifications to recombination physics affecting how cosmic microwave background patterns form, or systematic errors not yet identified in distance ladder calibrations. The S8 tension provides corroborating evidence that lambda CDM faces problems. Weak gravitational lensing surveys, measuring how mass concentrations distort background galaxy shapes, find S8 approximately 0.76, where S8 combines sigma 8, measuring density fluctuation amplitude on 8 megaparsec scales with matter density. Planck predicts S8 equals 0.83, a 2.5 to 3 sigma discrepancy. Lower S8 means the universe is less clumpy matter clusters less strongly than predicted. This connects to Hubble tension because structure growth depends on expansion rate. If true expansion rate is 73 rather than 67, structures would grow more slowly than lambda CDM predicts, for H0 equals 67, resulting in lower clumpiness and lower S8 matching observations. The Hubble and S8 tensions might share a common cause: incorrect expansion history in standard lambda CDM, affecting both distance measurements and structure formation. Early dark energy represents one proposed solution attempting to resolve Hubble tension. Early dark energy models add a scalar field contributing significant energy density around 50,000 years after the Big Bang, after radiation domination ended, but before matter domination fully established. This component decays rapidly, becoming negligible by 100,000 years and leaving no trace at recombination when cosmic microwave background formed. Early dark energy modifies expansion history in specific ways that increase inferred HAZARO from cosmic microwave background while leaving other CMB predictions nearly unchanged. Carefully tuned models can reduce Hubble tension to 2 to 3 sigma. However, early dark energy is theoretically ad hoc. No fundamental physics predicts it, and it doesn't fully resolve the tension. Furthermore, it worsens agreement with other observables, like the Lyman alpha forest power spectrum, measuring small-scale structure at high redshift, creating new tensions while partially resolving Hubble tension. Some cosmologists declared a crisis by 2019. A special issue of Nature Astronomy titled Cosmology's Crisis presented multiple perspectives. Some authors argued accumulated tensions indicate lambda CDM's failure, requiring new physics. Others argued tensions will resolve with better data or improved understanding of systematics. By 2024, the situation intensified. Hubble tension reached 5 to 6 sigma. S8 tension reached 5 to 3 sigma. Additional tensions appeared in galaxy cluster abundance, Lyman alpha forest measurements, and redshift space distortions. The accumulation of multiple tensions at 2 to 6 sigma across independent observables suggests systematic model failure rather than statistical flukes. But identifying which part of lambda CDM fails remains unclear. Dark matter properties, dark energy behavior, initial conditions, or something else entirely. The axis of evil in the cosmic microwave background. The cosmic microwave background should be statistically isotropic, its fluctuations showing no preferred direction or orientation. This expectation follows directly from the cosmological principle and inflationary cosmology, which predict initial fluctuations are random with no special axes. But in 2003, the Wilkinson Microwave Anisotropy Probe, known as WMAP, discovered something disturbing. The quadrupole and octupole moments, large-scale fluctuation patterns corresponding to spherical harmonics, with L equals 2 and L equals 3, are aligned with each other and with the ecliptic plane, the plane of Earth's orbit around the Sunday. They also align with the equinoxes, the points where the ecliptic crosses the celestial equator. This alignment pattern was dubbed the axis of evil by cosmologists who found it troubling. The probability of such alignment occurring randomly in an isotropic universe is less than 1 inch 10,000. The Planck satellite confirmed the alignment in 2013 using completely independent data and analysis, eliminating instrumental artifacts as explanation. Understanding what this means requires explaining spherical harmonic decomposition. The cosmic microwave background's temperature varies slightly across the sky. Regions differ by roughly 100 microkelvin from the average 2.725 Kelvin. These variations decompose into spherical harmonics, mathematical functions describing patterns on spheres analogous to how Fourier series decompose functions into sine and cosine waves. The dipole component, L equals 1, represents the largest scale variation and is dominated by our motion through space at 370 km per second. The quadrupole, L equals 2, represents the next largest scale, corresponding to patterns with 2 hot and 2 cold regions arranged opposite each other. The octupole, L equals 3, has 4 hot and 4 cold regions. These low L multipoles sample the largest physical scales, wavelengths comparable to the observable universe's size, and should be essentially random in standard inflationary models. The quadrupole and octupole shouldn't align. In an isotropic universe, their orientations should be uncorrelated, independent, random directions. But observations show they align remarkably well. The quadrupole's hot and cold regions lie roughly in the plane defined by the octupole's pattern. Furthermore, both align with the ecliptic plane, the plane containing Earth's orbit, to within about 5 to 10 degrees. They also correlate with the equinoxes, the 2 points per year when day and night have equal length. This is disturbing because the ecliptic and equinoxes are features of our local solar system's geometry, having nothing to do with cosmic structure 13.8 billion light-years across. The probability of random fluctuations producing this alignment pattern is calculated at less than 0.01%, meaning 99.99% of random universes wouldn't show such alignment. Multiple explanations have been proposed, none entirely satisfactory. One possibility is residual foreground contamination emission from our galaxy or solar system not perfectly removed during data analysis. WMAP and Planck teams exhaustively tested for this, analyzing data at multiple frequencies and using sophisticated component separation algorithms to isolate cosmic signal from foreground emission. The alignment persists after all foreground removal techniques. Another possibility is that we observe an atypical fluctuation. We happen to live in the rare 1-inch 10,000 universe, showing this alignment by pure chance. This is possible but unsatisfying, invoking anthropic reasoning without predictive power. A third possibility is that the cosmological principle, or inflation's assumptions, are violated on the largest scales, producing genuine anisotropy in initial conditions. This is theoretically disturbing because it requires modifications to well-established frameworks. Some researchers propose connections to large-scale structure orientation. If the cosmic web itself has preferred orientations on the largest scales, perhaps due to primordial gravitational waves, topological defects, or other exotic physics, then both cosmic microwave background anomalies and structure distribution asymmetries, like dipoles, might share a common origin. Testing this requires measuring whether structure alignments correlate with cosmic microwave background anomaly directions. Some studies find marginal evidence for such correlations, but statistical significance is weak and results depend sensitively on analysis methods. The idea remains speculative, but offers a potential link between different anomalies, suggesting they're symptoms of a single underlying deviation from standard cosmology, rather than independent rare flukes. The axis of evil challenges statistical isotropy at a fundamental level. Statistical isotropy means the universe's statistical properties, how likely fluctuations of various amplitudes and scales are, don't depend on direction. It's weaker than exact isotropy, allowing individual realizations, like our observed universe, to show some asymmetry, but requires asymmetries be consistent with statistical expectations. The quadrupole-octopole alignment is at the edge of, or beyond, statistical expectations, depending on precisely how probabilities are calculated. Different statistical tests give slightly different significance levels, but most yield probabilities around 0.1 to 1%. While not reaching 5 sigma certainty, this is uncomfortable. Standard cosmology predicts essentially no chance of such alignment, yet we observe it. Either we're unlucky, seeing a rare fluctuation, or something about largest scale cosmology differs from theory. No accepted physical mechanism explains the axis of evil. Proposed exotic explanations include cosmic topology, if space has non-trivial global topology, connecting distant regions or having finite volume. This could produce correlations on large scales. But cosmic topology models predicting the observed alignment require specific fine-tuned topologies without independent motivation. Another proposal involves primordial gravitational waves from inflation with non-standard properties, perhaps from anisotropic inflation models where expansion rates differ in different directions. Such models are theoretically possible but lack strong motivation from particle physics or quantum gravity. The lack of compelling physical mechanism makes the axis of evil a troubling loose end, an observational fact without theoretical explanation, hinting at physics beyond current understanding. Planck's 2013 confirmation eliminated hopes the anomaly would disappear with better data. Planck observed at 9 frequencies compared to WMAP's 5, with higher sensitivity and angular resolution. Planck's foreground removal techniques were more sophisticated, using the frequency dependence of different emission components to separate cosmic signal from galactic dust, synchrotron emission, free emission, and anomalous microwave emission. Despite these improvements, the quadrupole-octopole alignment remained, with essentially identical characteristics to WMAP's findings. This independent confirmation using different instruments and analysis methods strongly suggests the alignment is real astrophysical signal, not instrumental artifact or analysis error. The Planck collaboration devoted extensive investigation to the anomaly, ultimately concluding it's likely real, but noting that single universe observations cannot determine whether it's a rare fluctuation or indicates new physics. The philosophical implications are unsettling. The ecliptic is defined by Earth's orbit, a local feature of our solar system formed 4.6 billion years ago. The cosmic microwave background was emitted 13.8 billion years ago when the universe was 380,000 years old, long before the solar system existed. There's no causal connection. Cosmic microwave background photons didn't influence solar system formation, yet cosmic patterns on the largest scales align with local solar system geometry to high precision. This seems to violate the Copernican principle, the idea that we don't occupy a special location. One resolution is pure coincidence. The alignment is chance, and we notice it precisely because we define the ecliptic based on our local environment. But the low probability makes this unsatisfying. The axis of evil remains an unexplained mystery, a cosmic coincidence with no accepted explanation. Disturbing cosmologists who prefer predictive theories over mysterious alignments. The cold spot and Eridanus supervoid mystery. The cosmic microwave background's cold spot is a region approximately 10 degrees across, 20 times the Moon's apparent diameter, where temperature is about 70 microkelvin colder than surrounding regions. Discovered in 2004 by WMAP and confirmed by Planck, the cold spot is statistically unusual. Comprehensive simulations of isotropic Gaussian random fields, matching observed cosmic microwave background statistics, find that regions this cold and this large occur in fewer than 1 inch 1,000 simulations. The probability isn't negligible. It's not a 5 sigma anomaly, but it's uncomfortably low. The cold spot sits in the constellation Eridanus in the southern celestial hemisphere. Its existence has spawned numerous theories, ranging from mundane statistical fluctuations to exotic proposals involving collisions with parallel universes. The disturbing aspect is that no conventional explanation fully accounts for its properties despite 2 decades of investigation. The Eridanus supervoid provides a partial but incomplete explanation. Discovered in 2015 by Istvan Sapudi and colleagues, this supervoid is a large underdense region centered at redshift Z, approximately 0.22, corresponding to distance about 2.5 billion light-years, with diameter roughly 1.8 billion light-years. Galaxy surveys including Pan-STARRS-1 and WISE infrared observations show the region contains 20 to 30% fewer galaxies than cosmic average, a significant underdensity but not the most extreme known. When cosmic microwave background photons pass through an evolving underdense region, they gain energy falling into the potential, will then lose energy climbing out. If the void grows during transit due to cosmic expansion and dark energy, photons lose more energy climbing out than they gained falling in. This integrated Sachs-Wolf effect, known as ISW, produces a cold spot in the cosmic microwave background, aligned with the void. The problem is quantitative. The ISW effect from Eridanus supervoid predicts only 10 to 20 microkelvin temperature decrease, not the observed 70 microkelvin. Various groups have calculated the expected ISW signal using different void profiles and cosmic parameters. Most estimates fall in the 10 to 20 microkelvin range, with generous assumptions reaching perhaps 30 microkelvin. This leaves 40 to 50 microkelvin unexplained more than half the cold spot's depth. Either the cold spot results from multiple causes, the supervoid plus a rare primordial fluctuation coincidentally aligned, or the supervoid is more extreme than galaxy counts indicate, perhaps containing less dark matter than inferred from galaxy distributions. Neither explanation is entirely satisfying. The coincidence of a supervoid aligning with a rare primordial cold fluctuation seems contrived. But dark matter being distributed differently than galaxies suggest requires re-evaluating galaxy bias models. Alternative explanations venture into exotic territory. In 2007, Laura Massini-Houghton and colleagues proposed the cold spot might be a bruise from our universe colliding with a parallel universe in the multiverse. In eternal inflation models, universes bubble off from inflating space-time continuously, creating a multiverse of bubble universes. If two bubbles collided early in our universe's history, the collision might leave an imprint as a cold region in the cosmic microwave background. This idea is speculative and largely untestable. We have no independent evidence for other universes or mechanisms to detect them beyond the cold spot itself. The theory explains one anomaly by invoking a vast, untestable framework, which most cosmologists find unsatisfying despite its theoretical motivation from inflationary cosmology and string theory. Texture defects represent another exotic possibility. Topological defects, structures formed during phase transitions in the early universe, could include textures, which are field configurations that locally reduce energy density. If a texture existed at the surface of last scattering where the cosmic microwave background formed, it would create a cold region. Textures are predicted by some grand unified theories and have non-trivial topology, preventing them from unwinding. They would decay eventually, but might persist through recombination. The cold spot's circular symmetry and size are consistent with texture predictions. However, textures should produce additional signatures in cosmic microwave background polarization, specific patterns in how electric field directions of photons align. Polarization data from Planck don't show the expected signatures, weakening the texture explanation. Some researchers question whether the cold spot is genuinely anomalous or just an inevitable outcome of statistical fluctuations. The cosmic microwave background contains roughly 100,000 independent regions at the 1 degree scale where temperature can fluctuate independently. With 100,000 trials, a 1-inch 1,000 fluctuation, 3 sigma, in Gaussian statistics is actually expected to occur roughly 100 times. By this reasoning, finding one particularly cold region isn't surprising. The counter-argument is that the cold spot is special not just for being cold, but for being both unusually cold and unusually large, and for aligning with a supervoid. The joint probability of all these properties is lower than considering coldness alone. Detailed statistical analyses yield different conclusions depending on methodology, but most find joint probability in the 0.1 to 1% range uncomfortable but not definitive. The cold spot connects to broader concerns about cosmic microwave background isotropy. In addition to the cold spot and axis of evil, other anomalies include hemispherical power asymmetry, one hemisphere having slightly stronger fluctuations than the opposite, and parity asymmetry, odd and even multipoles having different statistical properties when they should be equivalent. Individually, each anomaly has marginal statistical significance around 2 to 3 sigma. Collectively, they suggest the cosmic microwave background isn't perfectly consistent with simple isotropic Gaussian predictions from standard inflation. Whether these anomalies represent genuine deviations requiring new physics or statistical fluctuations that will average out with better data remains debated. The cold spot is the most visually striking. You can see it clearly in temperature maps, making it particularly compelling despite not being the most statistically significant anomaly. Upcoming observations might clarify the mystery. The Simons Observatory and CMBS-4 experiment will map cosmic microwave background polarization with unprecedented precision. Polarization provides independent information about physical processes at recombination and during cosmic structure growth. Different explanations for the cold spot primordial fluctuations, ISW, from voids, textures, collisions, predict different polarization signatures. Matching observed polarization patterns against predictions will discriminate between models. Additionally, deeper galaxy surveys mapping structure around the cold spot and Eridanus supervoid will determine whether the supervoid is more extreme in dark matter content than galaxy counts suggest. If weak lensing shows significantly more underdensity than galaxy surveys, it would support supervoid-based explanations. If not, exotic alternatives gain credence. The cold spot epitomizes cosmology's current situation. Robust observations, revealing patterns not fully explained by standard models, but without conclusive evidence favoring specific alternatives. Lambda CDM doesn't predict the cold spot. It's improbable but not impossible within standard framework. This ambiguity frustrates cosmologists seeking definitive answers. Is the cold spot a clue to new physics, or just an unlucky fluctuation? We can't definitively answer with current data. The disturbing aspect isn't just the cold spot's existence, but the uncertainty it represents. Modern cosmology is precise enough to detect anomalies like this, yet not precise enough to definitively explain them, leaving unsettling loose ends that might be crucial clues or might be meaningless flukes. Only better data will resolve the ambiguity. The dipole in galaxy distribution contradicts isotropy. Multiple independent galaxy surveys reveal dipole asymmetries in structure distribution far exceeding what our motion through space should produce. These dipoles represent preferential concentration of matter in one direction across the observable universe. The radio galaxy dipole is approximately 4 times larger than the cosmic microwave background dipole caused by our 370 km per second motion. The quasar dipole is similarly excessive. Most disturbing different types of galaxies, radio galaxies, quasars, optical galaxies, X-ray selected clusters, show dipoles pointing in slightly different directions. If all dipoles resulted from our motion, they would point identically. If they resulted from a single cosmic asymmetry, they should align. The directional scatter suggests either systematic errors plague multiple surveys differently, or cosmic structure is so irregular on the largest scales that different galaxy populations sample different aspects of underlying asymmetry. The radio galaxy dipole was quantified by Ashok Singhal using 1.4 million sources from the NVSS and SUMS surveys covering northern and southern hemispheres. These surveys detect radio emission primarily from active galactic nuclei, where supermassive black holes power jets of relativistic particles. The dipole amplitude corresponds to approximately 1,500 km per second if interpreted kinematically as resulting from our motion. But our actual motion, measured through the cosmic microwave background dipole, is only 370 km per second toward right ascension, 168 degrees. Declination -7 degrees. The radio galaxy dipole points toward right ascension 170 degrees. Declination -7 degrees. Close in direction, but the amplitude is 4 times too large. This can't be explained by motion alone. suggesting genuine asymmetry in how radio galaxies distribute across the sky. Galaxy cluster dipoles add complexity and confusion. Different cluster catalogues yield different dipole directions and amplitudes. X-ray selected clusters from ROSAT observations show a dipole pointing roughly toward right ascension, 270 degrees opposite the radio galaxy dipole. Sunyaev-Zeldovich selected clusters from Planck observations show a dipole toward right ascension, 210 degrees. Optically selected clusters show yet another direction. The statistical significances are lower, around 2 to 3 sigma, but the directional inconsistency is troubling. If these dipoles are real, why don't they align? Possible explanations include selection effects, different observation methods preferentially detect different cluster populations which sample structure differently, or statistical flukes where small number statistics in high mass objects produce apparent signals that aren't genuine. Bulk flows provide another measure of large-scale asymmetry. Rather than counting galaxies, bulk flow measurements track coherent velocities, regions where many galaxies move together in the same direction, indicating gravitational attraction toward distant overdensities. The cosmic microwave background dipole indicates bulk flow at 370 km per second on scales comparable to the observable universe. Peculiar velocity surveys measuring galaxy distances through Tully-Fisher and fundamental plane relations find bulk flows of 600 to 800 km per second, extending to distances 300 to 500 million light-years. These flows are stronger and extend farther than lambda CDM predictions allow. While not reaching 5 sigma significance, the persistent excess across multiple surveys suggests structure on scales where models predict near homogeneity generates measurable anisotropic gravitational acceleration. The theoretical challenge is explaining dipole amplitudes without invoking structure exceeding the observable universe. If dipoles result from mass concentrations within the observable universe, those concentrations must be enormous superclusters containing 10 to the 16th solar masses or more, spanning billions of light-years. But such structures should be visible directly in galaxy surveys. Observations find large structures like the Shapley concentration and Laniakea supercluster, but their masses and distances don't fully account for observed bulk flows and dipoles. Some researchers propose dark flow, bulk flow, caused by gravitational attraction from mass beyond the observable universe's edge, outside our cosmic horizon. This idea is exotic, requiring structure formed before inflation or surviving through inflation in ways not predicted by standard inflationary models. Most cosmologists view dark flow skeptically, preferring to await better data before invoking physics beyond the observable universe. Some analyses find no dipoles, deepening the controversy. When Nathan Secrest and colleagues found the quasar dipole in 2020, other researchers reanalyzed the same data using different statistical methods and found no significant dipole or much weaker signals. The discrepancies stem from how foreground contamination is removed, how selection functions accounting for survey sensitivity are applied, and how statistical significance is calculated. Different choices yield different results, and no consensus methodology exists. This ambiguity allows both proponents and skeptics to claim their analyses are correct while dismissing opposing results as flawed. Until methodology standardizes or overwhelmingly strong signals appear resistant to analysis details, the dipole controversy will persist. The disturbing aspect is that multiple independent anomalies point toward large-scale anisotropy. The quasar and radio galaxy dipoles, the axis of evil alignment in the cosmic microwave background, the cold spot, hemispherical power asymmetry, and bulk flows collectively suggest the universe isn't perfectly isotropic on the largest scales. Individually, each has marginal significance, 2 to 4 sigma, leaving room for skepticism. Collectively, the probability that all are statistical flukes is lower. Some researchers calculate the joint probability of all observed anomalies at 1 inch, 10,000 or less, arguing this constitutes strong evidence for genuine anisotropy. Others argue that testing multiple hypotheses, looking for many possible anomalies, increases the chance of finding something rare by pure chance, reducing the combined significance. This look elsewhere effect is difficult to quantify rigorously in cosmology, leaving no clear resolution, the giant arc and other impossibly large structures. In 2021, Alexia Lopez discovered the giant arc, a structure spanning 3.3 billion light-years across, at redshift z equals 0.8, corresponding to a distance about 8 billion light-years. The structure consists of galaxies and galaxy clusters arranged in a near semicircle visible from Earth. The arc's physical size exceeds the Ricciarma limit, a theoretical maximum for structure sizes based on the cosmic horizon at recombination. The limit is approximately 1.2 gigaparsecs, or 3.9 billion light-years. Structures larger than this scale shouldn't exist according to standard inflation and lambda CDM, because larger fluctuations didn't have time to form before recombination. The giant arc approaches this limit, making its existence uncomfortable for theorists. If real, and not a projection effect or statistical fluke, it challenges inflation's predictions about maximum structure scales imprinted by quantum fluctuations during inflation. The Big Ring, discovered by the same team in the same sky region, adds to the problem. This structure is approximately 1.3 billion light-years across at similar redshift. Its proximity to the giant arc, both in location and redshift, is suspicious, suggesting possible chance alignment of unrelated structures. But the team argues the ring is a coherent structure based on overdensity statistics and connectivity analysis. The ring is smaller than the Ricciarma limit, but still uncomfortably large. The coincidence of two very large structures in the same region raises questions. Are we seeing a particularly rare patch of sky, or do such structures exist everywhere but are difficult to identify? Or are they projection effects, where multiple smaller structures align by chance, creating illusions of single large structures? The huge LQG, discovered by Roger Clowes and colleagues in 2013, claims to span 4 billion light-years. This large quasar group consists of 73 quasars at redshift Z, approximately 1.27, corresponding to about 9 billion light-years distance when the universe was 4.8 billion years old. The quasars cluster in a region much larger than lambda CDM allows. Statistical analysis showed 4 sigma significance for the structure's size exceeding predictions. However, significance is disputed. Critics recalculated, finding only 2 to 3 sigma, arguing the original analysis didn't properly account for look elsewhere effect. Furthermore, whether a loose association of quasars constitutes a single gravitationally bound or even causally connected structure is questionable. Quasars mark overdensities, but 73 quasars might sample multiple unrelated overdensities that happen to project near each other from our viewing angle. The Clowes-Campusano Large Quasar Group, discovered in 1991 and studied more thoroughly later, spans about 2 billion light-years and contains 18 quasars at redshift Z, approximately 1.3. Like the huge LQG, whether this constitutes a single structure is debated. The quasar's distribution could result from multiple filaments or walls roughly aligned with our line of sight. Three-dimensional connectivity analysis suggests the quasars do form a connected structure based on galaxy distributions, but the evidence isn't definitive. The persistent issue with quasar-based large structures is that quasars are rare. Only a small fraction of galaxies host quasars, so reconstructing underlying matter distribution from quasar positions is uncertain. Galaxy surveys with complete sampling are needed to definitively confirm or refute these structures. The homogeneity scale is supposed to be 300 to 400 million light-years. This is the scale where the universe becomes statistically homogeneous. The variance in matter density in spheres of this radius approaches zero as radius increases beyond this threshold. If structures exceeding 1 billion light-years exist, they violate this principle. Either the homogeneity scale is larger than thought, approaching 1 to 2 billion light-years, which requires rethinking fundamental cosmological assumptions, or these structures are rare statistical outliers at the extreme tail of lambda CDM's predictions, or they aren't genuine single structures but projection effects. None of these options is comfortable for theorists who prefer the universe to match well-established predictions from simple models. DESI observations should clarify whether these structures are real. DESI's spectroscopic survey maps galaxy distributions in 3 dimensions with unprecedented completeness and precision. If the giant arc, big ring, and large quasar groups are genuine gravitationally connected structures, DESI should see clear overdensities in galaxy distributions matching quasar and cluster locations. If they're projection effects, DESI will show that apparent structures in 2-dimensional projections actually consist of multiple smaller structures at different redshifts coincidentally aligned. First DESI papers addressing these structures should appear by 2025, providing definitive tests. Until then, the status of these impossibly large structures remains uncertain, disturbing cosmologists by suggesting our understanding of maximum structure sizes might be incomplete. The Shapley concentration pulling too hard. The Shapley concentration is the most massive structure in our cosmic neighborhood, a supercluster located approximately 650 million light-years away, containing roughly 10 million billion solar masses, about 10 times more massive than the Laniakea supercluster containing our Milky Way, comprising more than 25 major galaxy clusters and numerous groups. Shapley dominates local, large-scale gravitational dynamics. But disturbing observations suggest Shapley and surrounding structure can't fully explain the bulk flow observed in our region. Alexander Kashlinsky and colleagues reported in 2008 through 2010 a dark, flow, coherent bulk motion of galaxy clusters extending to 1 billion light-years with velocities 600 to 1,000 kilometers per second toward a direction roughly aligned with but not exactly matching Shapley's position. If real, this flow exceeds what Shapley's known mass should produce, suggesting gravitational attraction from additional mass concentrations beyond Shapley or perhaps beyond the observable universe's edge. The dark flow was detected using the kinematic Sunyaev-Zeldovich effect temperature shifts in the cosmic microwave background caused by hot gas in galaxy clusters moving relative to the CMB rest frame. When hot cluster gas moves toward us, CMB photons scattering off electrons gain energy, creating slightly higher temperature in that direction. When clusters move away, photons lose energy. By measuring temperature shifts for hundreds of clusters and averaging to suppress random motions, bulk flow coherent motion of many clusters together becomes detectable. Kashlinsky's team found clusters out to 1 billion light-years show coherent motion at 600 to 1,000 kilometers per second toward right ascension, approximately 270 degrees. Declination 30 degrees. This direction is roughly toward, but not exactly aligned with the Shapley concentration, suggesting additional structures contribute. The dipole repeller adds complexity to local dynamics. Discovered in 2017 by Yehuda Hoffman and colleagues, the dipole repeller is a large, underdense region, a supervoid, located in the opposite direction from Shapley. While Shapley gravitationally attracts nearby structure, including the local group containing the Milky Way, the dipole repeller pushes structure away through its gravitational repulsion. Underdense regions have less gravity, so structures fall away from them toward denser regions. The combination of Shapley pulling and the dipole repeller pushing creates net motion in the observed direction. This two-component model, pull plus push, explains local group motion better than Shapley alone. However, it doesn't fully account for bulk flows extending to 1 billion light-years. Structure beyond Shapley and the dipole repeller must contribute, but what structures and where they are remain uncertain. The dark flows reality is controversial. Multiple teams reanalyzed Kashlinski's data using different techniques and reached different conclusions. Some found no significant flow, others found weaker flows, others confirmed the original results. The discrepancies trace to how cosmic microwave background fluctuations are separated from kinematic Sunyaev-Zeldovich signals, how cluster positions and redshifts are determined, and how foreground contamination is removed. Different choices yield different results. Planck satellite data analysed for bulk flows found no significant detection, contradicting Kashlinski's claims. But Planck's analysis methods differed, and comparison is difficult. The lack of consensus leaves dark flows status uncertain, possibly real, possibly artifact of analysis, or possibly real but weaker than originally claimed. If dark flow is real, implications are profound. Coherent flows extending to 1 billion light-years suggest gravitational acceleration from mass concentrations well beyond where lambda CDM predicts homogeneity. Either homogeneity emerges at much larger scales than 300 to 400 million light-years, requiring revising the cosmological principle, or gravitational attraction comes from beyond the observable universe, mass outside our cosmic horizon, affecting us gravitationally but invisible because light from it hasn't reached us yet. The second possibility requires structure formation before or surviving through inflation in ways not predicted by standard inflationary models. It's exotic and theoretically uncomfortable, invoked only because conventional explanations seem insufficient. Laniakea's discovery revealed our place in the cosmic web, but didn't resolve flow anomalies, defined by R. Brent Tully and colleagues in 2014, using velocity flows. Laniakea supercluster spans 520 million light-years and contains 100,000 galaxies, including our Milky Way. The Great Attractor, located about 250 million light-years away in the direction of the Norma cluster, marks Laniakea's gravitational center, a concentration of mass pulling surrounding galaxies including us. But Laniakea doesn't explain all observed flows. The local group's motion includes components toward the Virgo cluster within Laniakea, toward Shapley beyond Laniakea's boundary, and away from the dipole repeller. The vectorial sum is complex, and uncertainties in masses and distances mean flow predictions don't precisely match observations. The mismatch isn't enormous, perhaps 100 to 200 kilometers per second discrepancy, but it's systematic, suggesting something about large-scale structure differs from models. Shapley's mass is well constrained through multiple methods. X-ray observations measuring hot gas properties, gravitational lensing mapping, total mass, galaxy velocity dispersions, indicating gravitational potential depth, and Sunyaev-Zeldovich measurements detecting hot gas all converge on Shapley's total mass, approximately 10 million billion solar masses. Given this mass and distance, 650 million light-years, gravitational acceleration at the local group's location is calculable, contributing roughly 200 to 300 kilometers per second to our motion. This accounts for about 25% of the local group's total 630 km per second motion relative to the cosmic microwave background. The Virgo cluster, much closer at 54 million light-years, contributes another 200 km per second. The dipole repeller adds perhaps 100 km per second. The sum is approximately 500 to 600 km per second, close to, but not exactly matching, observed 630 km per second. The residual suggests small additional structures contribute or systematic errors bias measurements, dark energy behaving differently across space. Dark energy was assumed to be the cosmological constant, perfectly uniform energy density filling all space, never changing, always exerting the same repulsive effect, driving cosmic expansion's acceleration. This assumption underlies lambda CDM cosmology, where lambda represents the cosmological constant. But in April 2024, the Dark Energy Spectroscopic Instrument collaboration released first-year results analyzing 6 million galaxies and quasars across cosmic time. Their measurement of dark energy's equation of state parameter W yielded -0.827, plus or minus 0.063, which is 2.5 sigma away from the cosmological constant value W equals -1. More disturbingly, when allowing W to vary with cosmic time, the data prefer models where W changes starting greater than -1 at high redshift and evolving toward more negative values approaching -1 today. This hints at quintessence, a dynamical dark energy field that evolves rather than Einstein's static cosmological constant. Understanding W requires understanding dark energy's properties. The equation of state relates pressure to energy density. W equals pressure divided by energy density. For ordinary matter, pressure is negligible compared to energy density, giving W approximately 0. For radiation, W equals 1/3. For vacuum energy, or a cosmological constant, quantum field theory predicts W equals -1, meaning negative pressure repulsion rather than attraction. Values of W slightly less negative than -1, like -0.9, represent quintessence, a scalar field slowly rolling down a potential, similar to the inflaton field during inflation but acting today. Values more negative than -1, like -1.1, represent phantom energy violating certain energy conditions and leading eventually to big rip scenarios where expansion accelerates unboundedly, tearing apart galaxies, stars, atoms, and eventually space-time itself. DESI's measurement of W equals -0.827 suggests dark energy might be weaker than cosmological constant predictions. If confirmed, this has profound implications. Structure formation is suppressed less by weaker dark energy, allowing more clustering and higher S8 values than lambda CDM predicts, potentially resolving the S8 tension where observations consistently find lower clumpiness than predicted. Weaker dark energy also affects cosmic expansion history, modifying distance redshift relations used in supernova cosmology and potentially contributing to Hubble tension. The 2.5 sigma significance isn't definitive. It could be statistical fluctuation or systematic error. But DESI's enormous sample size and careful systematic error analysis make the result difficult to dismiss. If W truly differs from -1, lambda CDM's foundational assumption fails, requiring cosmology to embrace dynamical dark energy models. Time variation in W is even more disturbing. When DESI allowed W to depend on redshift using parameterizations like W of Z equals W0 plus WA times Z divided by 1 plus Z, where W0 is today's value and WA characterizes evolution, the data preferred non-zero WA at approximately 2 sigma. The best fit shows W starting around -0.5 to -0.7 at redshift, Z equals 2, when the universe was 3.3 billion years old, then evolving toward -1 today. This pattern is called thawing quintessence. The field was nearly frozen in the early universe, but is now becoming more dynamical. Alternatively, freezing quintessence models, where W starts closer to -1 and becomes less negative, also fit data reasonably. The key point is that constant W equals -1 fits worse than time-varying models, suggesting dark energy's nature changes across cosmic history. Phantom crossing represents the most exotic possibility. Some DESI analyses, allowing very flexible W of Z, find evidence for phantom crossing W, changing from greater than -1 at high redshift to less than -1 at low redshift, crossing exactly -1 at some intermediate epoch. Phantom crossing is theoretically difficult to achieve in simple scalar field models because it typically requires violating null energy condition, a fundamental assumption in general relativity stating that energy density plus pressure should be non-negative. Violating this condition allows exotic phenomena like wormholes and time machines. Most physicists are skeptical of phantom crossing because it requires such exotic physics, but data hints at it nonetheless. If future data confirm phantom crossing, cosmology faces radical rethinking of dark energy's nature. Anisotropic dark energy pressure represents another disturbing possibility. Some researchers propose dark energy might have different pressures in different directions, exerting stronger repulsion along some axes and weaker repulsion perpendicular. This would violate isotropy, creating preferred directions in cosmic expansion. While exotic, anisotropic dark energy could simultaneously explain multiple anomalies. The axis of evil through anisotropic initial conditions influenced by directional dark energy, dipoles through direction-dependent expansion rates, and S8 tension through different structure growth rates along different axes. Testing requires measuring expansion rates and structure growth separately in different sky directions. Current data provide marginal hints of anisotropic expansion, but systematic errors and selection effects make interpretation ambiguous. Definitive tests await next-generation surveys with better sky coverage and control of systematics. Quintessence models vary widely in predictions and theoretical motivation. Tracker quintessence models have potentials designed such that the scalar field automatically adjusts to track dominant energy components during cosmic history, tracking radiation in early universe, then matter, finally becoming dominant itself, driving acceleration. These models are theoretically attractive because they avoid fine-tuning initial conditions. K-essence models include non-standard kinetic terms in the scalar field Lagrangian, allowing W to vary based on field velocity rather than potential shape. Coupled quintessence models allow the dark energy field to interact with dark matter or ordinary matter, exchanging energy and modifying structure formation in testable ways. Each model makes specific predictions for W of Z evolution, structure growth, and other observables, allowing data to discriminate between them. The risk is that W measurements suffer from systematic errors not yet identified. Distance determinations rely on standard candles, like type Ia supernovae, and baryon-acoustic oscillations. If systematic errors bias distance estimates, perhaps through dust extinction, supernova evolution with redshift, or selection effects, inferred W values will be wrong. DESI carefully studied these systematics, varying assumptions, and cross-checking with independent datasets. The W equals -0.827 result persists across different analysis choices, suggesting robustness. However, unknown unknowns, systematic errors not yet conceived, could still lurk. The history of cosmology includes multiple claimed detections, later explained by systematics. The community remains appropriately cautious, requiring independent confirmation before declaring cosmological constant overthrown. Upcoming surveys will test DESI's findings. The Euclid Space Telescope, launched in 2023, will map billions of galaxies over 15,000 square degrees, measuring distances through baryon-acoustic oscillations and weak gravitational lensing. The Nancy Grace Roman Space Telescope, launching in 2027, will conduct deep, wide-area surveys optimized for measuring dark energy through multiple complementary methods. The Vera-C, Rubin Observatory's legacy survey of space and time, starting 2025, will image the entire southern sky every few nights for 10 years, mapping billions of galaxies and measuring distances. These surveys will measure W with precision, several times better than DESI, definitively determining whether W equals -1 or deviates. If multiple independent surveys confirm W differs from -1, the cosmological constant is dead, and cosmology enters a new era of understanding dark energy as dynamical rather than constant. The integrated Sachs-Wolf effect anomalies. The integrated Sachs-Wolf effect should provide a powerful test of dark energy's properties through cross-correlating cosmic microwave background temperature fluctuations with large-scale structure maps. When CMB photons travel through evolving gravitational potentials, such as those created by voids and superclusters, growing or decaying as dark energy affects structure evolution, they gain or lose energy. Imprinting temperature shifts on the CMB correlated with structure positions. Dark energy causes potentials to decay as expansion accelerates, making voids less underdense and overdensities less overdense over time. This decay produces ISW signals. Photons crossing voids should appear slightly warmer, photons crossing superclusters slightly cooler compared to average. Observations should show strong correlations between CMB temperature and galaxy positions. But measurements consistently find ISW correlations 2 to 3 sigma weaker than lambda CDM predicts, suggesting dark energy behaves differently than standard models assume, or structure evolution differs from predictions. The basic ISW physics is straightforward. A CMB photon traveling through a gravitational potential well loses energy falling in and gains energy climbing out. If the potential doesn't change during transit, energy loss and gain exactly cancel, producing no net effect. But if dark energy causes cosmic expansion to accelerate, structure growth slows and gravitational potentials decay, wells become shallower, hills become flatter. A photon falling into a deep well but climbing out of a shallower well gains net energy, appearing slightly hotter. Conversely, photons crossing decaying overdensities lose net energy, appearing cooler. The ISW effect thus creates temperature anisotropies correlated with large-scale structure positions, with correlation strength depending on dark energy properties, controlling how fast potentials decay. Cross-correlation measurements require matching CMB temperature maps with galaxy catalogues. The Dark Energy Survey measured correlations between Planck CMB data and 100 million DES galaxies spanning redshifts 0.2 to 1, finding correlation amplitudes about 30% lower than lambda CDM predictions with 2.5 sigma significance. The BOSS survey cross-correlated with Planck found similar deficits at 2 to 3 sigma. The two MASS and WISE infrared galaxy surveys also show weaker than predicted ISW signals. The consistency across multiple independent galaxy surveys using different selection methods and covering different redshift ranges suggests the deficit is real rather than specific to one dataset. The combined statistical significance across all surveys reaches approximately 3 sigma, uncomfortably high, to dismiss as pure chance, but not reaching 5 sigma certainty required for definitive claims. Void ISW correlations specifically test dark energy in underdense regions. Voids are simpler than clusters, less affected by baryon physics, like feedback from supernovae and active galactic nuclei, making theoretical predictions more robust. Multiple studies identified voids in galaxy surveys like SDSS and measured CMB, temperature averaged over void positions, finding warm spots as expected from ISW. However, the measured temperature excess is consistently 30 to 40% lower than lambda CDM predicts. Some researchers propose this indicates voids are less empty in dark matter than galaxy distributions suggest, with dark matter distributions differing from galaxy distributions due to environmental effects on galaxy formation. Others suggest dark energy behaves differently in voids, perhaps exerting less repulsion in underdense regions, violating the assumption that dark energy density is perfectly uniform across space. Supercluster ISW correlations show the opposite anomaly. Where voids produce weaker ISW signals than predicted, superclusters produce stronger signals. Measuring CMB temperature at supercluster positions yields cold spots about 20% larger than lambda CDM predicts at 2 sigma significance. This opposite behavior, voids too warm, superclusters too cold, is puzzling. If dark energy is uniform, both should deviate in the same direction and magnitude. The opposite deviations suggest structure-dependent dark energy or systematic errors affecting void and supercluster samples differently. Alternatively, potentials might decay faster in overdense regions and slower in underdense regions than standard gravity predicts, hinting at modified gravity models where gravitational strength depends on environment. Modified gravity models attempt to explain ISW anomalies. In f of r gravity, an additional term proportional to some function f of the Ricci scalar r modifies Einstein's equations. These models can mimic dark energy's effects on expansion while predicting different structure, evolution, and ISW signals. DGP gravity, named after Dvali, Gabadadze, and Parati, involves extraspatial dimensions causing gravity to weaken on large scales, again mimicking dark energy, but with different ISW predictions. Some modified gravity models predict weaker ISW signals, matching observations better than lambda CDM. However, these models face constraints from other observables, solar system tests of gravity, galaxy rotation curves, gravitational wave propagation speeds, requiring fine-tuned parameters to satisfy all constraints while explaining ISW anomalies. Most cosmologists view modified gravity skeptically, preferring simpler lambda CDM explanations if systematic errors or dark energy variations can account for ISW discrepancies. Dark energy coupling to matter represents another theoretical possibility. In coupled quintessence models, the dark energy scalar field interacts with dark matter or baryons, transferring energy and momentum. This coupling affects structure growth differently than standard lambda CDM, where dark energy and matter evolve independently. Coupling can suppress or enhance structure formation depending on sign and strength, modifying ISW signals. Some coupled models predict ISW amplitudes closer to observations than uncoupled lambda CDM. However, coupling typically introduces fifth forces, additional fundamental forces mediated by the dark energy field, which face stringent constraints from laboratory tests and astrophysical observations. Achieving observable ISW effects while satisfying fifth force constraints requires carefully designed couplings, often invoking screening mechanisms that hide fifth forces on small scales while allowing them on cosmological scales. Systematic errors might explain apparent ISW anomalies. Cross-correlations require accurately matching spatial positions of CMB features and galaxy overdensities. If galaxy surveys have incomplete sky coverage, selection effects, biasing which galaxies are detected, or photometric redshift errors causing position uncertainties, cross-correlation amplitudes could be systematically biased. Cosmic microwave background foreground contamination emission from our galaxy's dust, synchrotron, and free emission not perfectly removed could add noise or bias to CMB temperature maps, diluting cross-correlation signals. Multiple studies tested these systematics extensively, varying analysis methods and using different datasets. Yet the ISW deficit persists. Either systematics are more subtle than appreciated, affecting all analyses similarly, or the effect is genuine, indicating lambda CDM inadequacies. Future observations will clarify ISW anomalies. Next-generation CMB experiments like CMB-S4 and Simon's Observatory will map temperature and polarization with higher sensitivity and better foreground removal than Planck. Upcoming galaxy surveys like Euclid and LSST will provide far larger galaxy samples with better redshift measurements, improving cross-correlation signal-to-noise by factors of 3 to 5. Combined, these datasets will measure ISW correlations with precision sufficient to distinguish between lambda CDM, modified gravity, coupled dark energy, and systematic error scenarios. If ISW deficits persist and strengthen with better data, lambda CDM faces serious challenges requiring fundamental modifications. If deficits disappear, current anomalies will be attributed to statistical fluctuations or subtle systematics, vindicating standard cosmology. Primordial non-Gaussianity hints in structure. Inflation predicts initial density fluctuations should be Gaussian, their statistical distribution matching a bell curve with specific properties. Deviations from Gaussianity, called primordial non-Gaussianity, would indicate exotic physics during inflation, such as multi-field models, non-standard kinetic terms, or interactions between the inflaton field and other fields. The cosmic microwave background provides the most direct test, measuring non-Gaussianity through the FNL parameter, quantifying the amplitude of non-Gaussian contributions. Planck satellite measurements constrain FNL, consistent with 0 within uncertainties. FNL equals minus 0.9 plus or minus 5.1 for local type non-Gaussianity. However, large-scale structure measurements analyzing galaxy clustering find marginal hints of non-zero FNL at values 10 to 50, creating 2 to 3 sigma tensions between CMB and structure-based constraints. If primordial fluctuations are non-Gaussian, it reshapes understanding of inflation and could explain some cosmic web anomalies. Local type non-Gaussianity affects structure formation in specific ways. In Gaussian models, galaxy clustering depends only on dark matter distribution. With non-Gaussianity, galaxy clustering gains scale-dependent bias. The ratio of galaxy density fluctuations to dark matter fluctuations varies with scale. On large scales exceeding 100 million light-years, non-Gaussianity enhances galaxy clustering proportional to FNL, making galaxies cluster more strongly than dark matter predicts. On small scales below 10 million light-years, effects are negligible. This scale-dependent signature allows testing non-Gaussianity using galaxy surveys measuring clustering at various scales. Theoretical predictions by Asantha Kure, Nyayesh Afshordi, Uro Selyak, and Matthias Zaldaraiga, starting in 2008, showed that FNL equals 100 produces detectable, scale-dependent bias observable in surveys like SDSS. Measurements from galaxy clustering yield FNL values higher than CMB constraints. Analysis of SDSS quasar clustering by Slosar and colleagues found FNL equals 50 plus or minus 30 consistent with 0, but with best fit significantly positive. BOSS Galaxy Survey analysis found FNL equals 20 to 40 depending on scale, range, and galaxy sample used, with 2 sigma preference for non-zero values. DESI preliminary results hint at similar FNL, approximately 30, with 2 sigma significance. These structure-based measurements are consistently higher than Planck's FNL, consistent with 0, creating tension. The discrepancy could indicate systematic errors in structure analyses, perhaps incorrectly modelled galaxy bias or redshift space distortions mimicking non-Gaussianity signals. Alternatively, CMB and structure probe non-Gaussianity differently, and the tension reveals new physics not captured by simple, local-type models. Multi-field inflation models naturally produce non-Gaussianity. Single-field slow-roll inflation, the simplest model with one scalar field, slowly rolling down a smooth potential, predicts nearly Gaussian fluctuations with FNL, much less than 1, far below observational limits. But models with multiple scalar fields, called multi-field inflation, or curvaton models where additional fields contribute to density fluctuations, can generate FNL values 10 to 100. During inflation, quantum fluctuations in multiple fields create correlated perturbations that later convert to density fluctuations through non-linear processes, producing non-Gaussian patterns. Observing FNL approximately 10 to 50 would provide strong evidence for multi-field inflation, revealing that inflation involved richer dynamics than minimal single-field models. Non-Gaussianity could explain some large-scale structure anomalies. Non-Gaussian initial conditions with FNL approximately 50 enhance large-scale clustering, making the most massive structures form earlier and grow larger than Gaussian models predict. This could partially explain the excess of large voids and giant structures like the giant arc and huge LQG that seem too large for lambda CDM. Non-Gaussianity also affects the galaxy distribution's dipole and higher order moments, potentially contributing to observed asymmetries. However, detailed calculations show non-Gaussianity alone can't explain all anomalies. Effects are too small to account for observed dipole amplitudes or cold spot properties. Non-Gaussianity might be one ingredient in a multi-component solution involving non-Gaussianity plus dark energy variations plus modified gravity. Tensions between CMB and large-scale structure non-Gaussianity constraints disturb cosmologists. CMB provides a direct snapshot of conditions 380,000 years after the Big Bang, when fluctuations were small and linear theory applies. Structure formation involves gravitational collapse, producing nonlinear effects, potentially contaminating non-Gaussianity measurements. Galaxy formation adds additional nonlinear processes and biases. Perhaps structure-based FNL measurements are systematically biased by these complexities, incorrectly attributing nonlinear structure formation effects to primordial non-Gaussianity. Testing requires better models of galaxy bias, incorporating non-linear effects, baryon physics, and environmental dependencies. Simulations including these complexities are improving but remain imperfect, leaving systematic uncertainties that obscure whether structure-based FNL excesses are real or artifacts. Upcoming surveys will decisively test primordial non-Gaussianity. Euclid and LSST will map billions of galaxies across large volumes with excellent redshift measurements, measuring scale-dependent bias with precision 5 to 10 times better than current surveys. This will constrain FNL to approximately plus or minus 1 to 2, rivaling or exceeding CMB precision. CMB S4 will measure CMB non-Gaussianity with improved sensitivity, reducing FNL uncertainties to approximately plus or minus 2. If both CMB and structure measurements converge on FNL consistent with 0, non-Gaussianity is ruled out and single-field inflation is favoured. If both find FNL approximately 10 to 30, multi-field inflation is confirmed. If discrepancies persist, CMB finding 0, structure finding 20, cosmology faces a crisis, requiring explanations for why different probes yield inconsistent results. Simulations failing to match observations. State-of-the-art cosmological simulations represent pinnacles of computational astrophysics. The illustrious TNG, Eagle, Magneticum, and Simba projects evolved billions of particles through cosmic time using supercomputers running for months, incorporating dark matter, gravity, gas, hydrodynamics, star formation, supernova feedback, active galactic nuclei feedback, magnetic fields, and radiative cooling. These simulations successfully reproduce many observed galaxy properties: stellar masses, colors, morphologies, and clustering. Yet systematic discrepancies persist when comparing simulation predictions to cosmic web observations. Galaxy cluster properties differ by 10 to 15%. Filament density profiles mismatch by 20 to 30%. Void statistics are inconsistent by 20 to 30%. These aren't catastrophic failures, but consistent offsets across multiple independent observables suggest missing physics, incorrect assumptions about initial conditions or dark matter properties, or computational limitations preventing accurate modelling of relevant scales. Galaxy cluster abundance provides a particularly troubling test. Clusters are rare, the most massive gravitationally bound structures in the universe, making them sensitive probes of cosmology. Their abundance depends on cosmological parameters: matter, density, dark energy, initial fluctuation amplitude. Lambda CDM predicts specific numbers of clusters above various mass thresholds as functions of redshift. Observations from X-ray surveys, Sunyaev-Zeldovich surveys, and optical surveys consistently find 20 to 30% fewer massive clusters above 10 to the 15th solar masses than Lambda CDM predicts using parameters from Planck CMB observations. This cluster abundance tension reaches 2 to 3 sigma significance and connects to S8 tension lower. S8 means less clumpy universe, producing fewer massive clusters. Simulations using Planck parameters predict cluster abundances matching Lambda CDM but disagreeing with observations. Filament density profiles show systematic mismatches between simulations and weak lensing observations. Simulations predict dark matter density in filament cores peaks at roughly 2 to 3 times cosmic average density, declining smoothly with distance from the filament axis. Weak lensing measurements from Subaru HSC and Dark Energy Survey show core densities 20 to 30% higher, roughly 2.5 to 4 times cosmic average, with steeper declines. The excess isn't huge, but its consistency across independent observations and different filaments suggests systematic simulation inadequacies. Possible explanations include that simulations underestimate how effectively gas and dark matter channel into filaments during structure formation, or that dark matter's properties differ from simple collisionless cold dark matter assumed in simulations, perhaps self-interacting dark matter that behaves differently in filament environments. Void statistics reveal consistent discrepancies. Simulations predict void size distributions, how many voids of each size exist, that decline exponentially beyond certain scales. Observations show the distribution's tail extends farther, with more large voids than predicted. The mismatch is quantified as 20 to 30% excess in void number counts above 1 billion light-years compared to simulation predictions. Similarly, void density profiles how matter distributes within voids, show voids are emptier at their centers than simulations predict. These discrepancies might indicate that galaxy formation in voids is suppressed more than models assume, making voids appear emptier when using galaxy counts to identify them. But weak lensing void statistics also show similar discrepancies, suggesting the problem isn't purely galaxy formation, but involves total matter, including dark matter. Baryon feedback uncertainties plague simulation predictions. Supernovae explosions and active galactic nuclei inject energy into gas, heating it and driving outflows that remove gas from galaxies and redistribute it throughout filaments and voids. These processes significantly affect structure on scales 1 to 100 million light-years, modifying galaxy masses, star formation rates, and gas distributions. Different simulations implement feedback differently using different supernova energy prescriptions, different AGN accretion models, different outflow speeds, yielding predictions varying by 20 to 50%, despite using identical cosmological parameters. This spread indicates fundamental uncertainties in modeling complex astrophysical processes that dominate on small scales but affect larger scale structure through redistribution of baryons. AGN feedback models vary widely across simulations. Illustris TNG uses a two-mode AGN model with thermal energy injection at low accretion rates and kinetic jets at high rates. Eagle uses purely thermal feedback with Bondi-Hoyle accretion. Magneticum includes jet precession and anisotropic energy injection. Simba uses kinetic jets always. Despite all producing reasonable galaxy populations, these models predict different gas distributions in filaments, different cluster properties, and different void characteristics. When predictions disagree by 15 to 30% across simulations, using different feedback implementations but identical cosmology, it reveals that astrophysical uncertainties dominate over cosmological parameters on relevant scales. Untangling cosmological signals from astrophysical systematics requires either better understanding of baryon physics or observables less sensitive to baryons. Resolution limitations affect simulations despite enormous computational resources. Illustris TNG's highest resolution run resolves dark matter particles with masses 7 million solar masses and gas cells with 1.4 million solar masses allowing galaxies down to 100 million stellar masses to form self-consistently. But this is still insufficient for resolving individual stars, stellar feedback on small scales, or turbulence cascading down to parsec scales. Subgrid models approximate unresolved physics, introducing parameters tuned to match observations. Different tunings yield different large-scale predictions, even within a single simulation code. Comparing simulations with different resolutions shows predictions converge slowly, suggesting truly converged results require even higher resolution beyond current computational capabilities. Cosmic web topology measurements reveal subtle but systematic mismatches. Genus statistics measure cosmic structures' connectedness, how many holes versus islands exist in density distributions at various thresholds. Observations find the cosmic web is slightly more sponge-like than simulations, predict more connected, fewer isolated overdensities. Minkowski functionals characterizing structures' geometrical properties show similar discrepancies. These topology differences don't dramatically affect overall structure appearance, but hint at subtle failures in how simulations model structure formation physics. Possible causes include incorrect assumptions about initial conditions, perhaps primordial non-Gaussianity, or scale-dependent features not captured by simple power law power spectra, or missing physics like modified gravity, or dark matter self-interactions affecting structure connectivity. The persistent Earth term anomaly appears in both simulations and observations, but with different amplitudes. In galaxy power spectrum measurements, a term called the Earth term represents correlations arising from observational geometry and selection effects. Theoretical models predict specific Earth term amplitudes based on survey characteristics. Observations consistently measure Earth terms 10 to 20% larger than predicted. Simulations processed through identical observational pipelines show the same excess, suggesting the problem isn't cosmological, but relates to how surveys sample structure. Yet, despite extensive investigation, no explanation fully accounts for the excess. This unresolved systematics issue affects cosmological parameter constraints and demonstrates that even well-studied measurements harbor unexplained effects, limiting precision. Upcoming simulations will test whether discrepancies persist. The Flamingo project plans simulations 8 times higher resolution than illustrious TNG, evolving volumes up to 5 billion light-years across, with systematic exploration of baryon feedback variations. Millennium TNG will simulate similar volumes with alternative dark matter models, including warm dark matter and self-interacting dark matter. These next-generation simulations will determine whether current mismatches result from insufficient resolution or alternative physics. If high-resolution simulations with standard physics match observations, current discrepancies are computational artifacts. If mismatches persist despite better resolution and extensive feedback variations, it strongly suggests missing fundamental physics, modified gravity, alternative dark matter, or exotic dark energy behaviors not included in lambda CDM. What the disturbing patterns might mean. Cosmology faces a crisis involving multiple tensions at 2 to 6 sigma significance across independent observables. The Hubble tension is 5 to 6 sigma. The S8 tension is 2.5 to 3 sigma. Cluster abundance is 2 to 3 sigma discrepant. ISW effect is 2 to 3 sigma weaker than predicted. Large-scale asymmetries appear at 3 to 5 sigma. Voids and filaments deviate from predictions at 2 to 3 sigma. Individually, each might be statistical fluctuation or systematic error. Collectively, the probability all are flukes approaches 1 in millions. Lambda CDM cosmology, the standard model of cosmology, combining cold dark matter, cosmological constant dark energy, and inflationary initial conditions, successfully explains the cosmic microwave background, Big Bang nucleosynthesis, galaxy clustering on intermediate scales, and many other phenomena, yet it strains to simultaneously accommodate all recent precision observations. Either systematic errors affect multiple independent measurements in ways not understood, or Lambda CDM requires modifications or extensions incorporating new physics. Early dark energy represents one leading solution, attempting to relieve Hubble tension. Standard Lambda CDM has dark energy becoming important only around 5 billion years ago, when the universe was 9 billion years old. Early dark energy models add a component contributing 5 to 10% of total energy density around recombination at 380,000 years, then rapidly decaying to negligibility by 1 million years. This component modifies the sound horizon, the distance sound waves travelled before recombination, which is imprinted in cosmic microwave background, angular scales, and baryon acoustic oscillations. Reducing the sound horizon increases the Hubble constant inferred from CMB, while leaving most other CMB predictions nearly unchanged. Carefully designed early dark energy models reduce Hubble tension from 5 sigma to 2 to 3 sigma. However, they create new tensions with other observables and lack compelling theoretical motivation. No fundamental physics predicts early dark energy at the required density and decay rate. Modified gravity offers alternative approaches, replacing or supplementing general relativity on cosmological scales. F of R gravity adds terms to the Einstein-Hilbert action proportional to functions of the Ricci scalar, modifying gravitational field equations. These modifications can mimic dark energy's effects on cosmic expansion while predicting different structure growth rates, potentially resolving S8 tension by suppressing structure formation. DGP gravity involves extra dimensions causing gravitational leakage, weakening gravity on large scales and producing self-accelerating expansion without dark energy. Galilean models use scalar fields with derivative self-interactions, producing screening mechanisms that hide modifications on solar system scales while allowing them cosmologically. Each model faces observational constraints from solar system tests, galaxy dynamics, gravitational wave speeds measured from neutron star mergers, and CMB observations. Satisfying all constraints while explaining cosmological tensions requires fine-tuning parameters, reducing theoretical appeal. Interacting dark sectors propose that dark matter and dark energy exchange energy and momentum through coupling terms in their governing equations. Standard Lambda CDM assumes dark matter and dark energy evolve independently. Coupled models allow energy transfer, modifying expansion history and structure growth simultaneously. Depending on coupling sign and strength, interactions can suppress or enhance structure formation at different scales and epochs, potentially reconciling Hubble and S8 tensions together. Couplings typically introduce fifth forces mediated by dark energy fields, constrained by fifth force experiments and stellar dynamics. Screening mechanisms like chameleon or symmetron fields hide fifth forces in high-density environments while allowing them in cosmic voids, enabling observationally viable coupled models. Testing requires precise measurements of structure growth across multiple redshifts, comparing with expansion history measurements to detect coupling signatures. Systematic errors remain the most conservative explanation. Cosmological measurements are extremely challenging, requiring understanding astrophysical systematics, instrumental calibrations, selection effects, and theoretical modelling uncertainties. Cepheid distance ladder measurements assumes Cepheid period luminosity relations are universal and metallicity effects are correctly modelled. Type Ia supernova cosmology assumes supernovae are standard candles with understood colour and stretch corrections, and dust extinction is accurately modelled. Weak lensing assumes galaxy shape measurements are unbiased and intrinsic alignments are correctly subtracted. Cluster abundance assumes mass estimates from X-ray, Sunyaev-Zeldovich, or weak lensing are accurate and selection functions are well understood. Each measurement involves dozens of potential systematics, any of which might introduce biases. Perhaps multiple systematics conspire, biasing different measurements in directions that create apparent tensions when none exist physically. Distinguishing between systematic errors and new physics requires consistency tests across diverse datasets. If Hubble tension results from systematic errors in Cepheid distances, alternative distance indicators like tip of the red giant branch stars should disagree with Cepheids. Instead, they agree, suggesting Cepheid systematics aren't the full answer. If S8 tension results from weak lensing systematic errors, cluster abundance measurements using different mass estimation techniques should disagree. Instead, they agree, suggesting weak lensing systematics aren't the full answer. The consistency across multiple independent probes strengthens the case for new physics. However, consistency doesn't prove new physics. Multiple measurements might suffer correlated systematics not yet identified. Upcoming observations with improved systematic error control will discriminate between scenarios. The Nancy Grace Roman Space Telescope launching in 2027 will revolutionize cosmology through wide-field infrared imaging and spectroscopy. Roman will measure type Ia supernova distances at redshifts exceeding Z equals 2, far beyond current surveys reaching Z approximately 1.5, providing crucial tests of dark energy evolution. Roman will conduct weak lensing surveys covering 2,000 square degrees to depths detecting billions of faint galaxies, measuring S8 with precision 3 times better than current surveys. Roman will measure baryon acoustic oscillations in galaxy clustering across cosmic time with percent-level precision, constraining expansion history independently of supernova and CMB. These measurements will determine whether tensions are real or systematics by providing completely independent probes of the same physical quantities with different systematic error budgets. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, starting in 2025, will image the entire southern sky repeatedly for 10 years, detecting approximately 20 billion galaxies. LSST will discover millions of supernovae, measure weak lensing for billions of galaxies, track millions of variable stars, including Cepheids, and create three-dimensional maps of cosmic structure across half the sky. The sheer statistical power factors of 10 to 100 more data than current surveys will reduce statistical uncertainties to sub-percent levels for many observables. If tensions persist with such enormous datasets and multiple independent methods yield consistent results, systematic error explanations become increasingly implausible, forcing acceptance of new physics beyond lambda CDM. The Euclid mission, launched in 2023 by the European Space Agency, will map galaxies across 15,000 square degrees, measuring shapes and distances for billions of galaxies. Euclid's primary science goals are measuring dark energy properties through weak lensing and baryon acoustic oscillations with unprecedented precision. Euclid will constrain W to approximately 2% precision and its time evolution WA to 10%, definitively testing whether dark energy is the cosmological constant or dynamical quintessence. Euclid will measure S8 with 1% precision through weak lensing tomography, splitting galaxies into redshift bins and measuring lensing separately in each, reconstructing how structure evolved across cosmic history. Comparing Euclid's measurements with Planck's predictions will provide the ultimate test of lambda CDM's structure formation model. A paradigm shift or refinement awaits, but which? If upcoming surveys confirm tensions and demonstrate new physics is required, cosmology undergoes paradigm shift comparable to the 1998 discovery of dark energy acceleration, fundamentally revising understanding of cosmic evolution. If tensions resolve through better systematics understanding or disappear with improved data, lambda CDM is refined and solidified, vindicating decades of theoretical work. The disturbing patterns currently observed, excessive large-scale asymmetries, anomalous voids and filaments, multiple statistical tensions, represent either the first cracks in lambda CDM's foundation or the last hurdles before complete validation. Within 5 to 10 years, Roman, LSST, Euclid, and CMBS-4 data will answer definitively. Until then, cosmologists face unsettling ambiguity. Knowing the universe presents patterns, not fully explained, but unable to determine whether those patterns herald revolution or merely reflect observational challenges at the frontier of cosmology's precision.